With Lecture 5, we're going to start our Chapter 3 material. We're going to take a look at naming ionic and molecular compounds. We're going to kind of start with a little reminder of what molecular compounds are, how to identify them, and the same with ionic compounds. Some important announcements. Chapter 3, there's only one chapter of homework due this weekend. We're only going to cover Chapter 3 this week. So Chapter 3 homework will be due on Sunday, May 31st at midnight. I still will have office hours today, Tuesday, and Thursday, 12 to 1:30 p.m. on Blackboard Collaborate. Please let me know if you need any help with the material or need any help with the homework. That's what those office hours are for. So far, they've been pretty quiet. So, this is something you guys are paying for. I am here to help. I'm certainly happy to help as well. Also, I took a little bit of time over the weekend to read all the feedback about the course survey that I asked, the quick question of just how is this course working so far for you. I really do appreciate that. Thank you very much for taking the time to kind of let me know how the course is working, because this is all new to me, and I really do appreciate the feedback, because really I want to make this as best as possible it can be for you, and it's a learning experience for me as well. So for today's lecture, we're going to help differentiate between ionic and molecular compounds, and we're also going to look at naming ionic and molecular compounds. And as you'll see in a little bit, you already know how to name ionic compounds, because we know many ionic compounds. We know those names, and we're just going to go over the rules of how to name these ionic compounds. But first, a little reminder of chemical formulas and what a chemical formula represents. We've looked at formulas, and we talked about them a little bit when we were talking about the molar mass of something, right? The mass I would need to have a mole of that compound. So a chemical formula represents how many of each element are present, right, in that compound. And so this glucose example, right, what all that means, all these subscripts mean, is that I have 6 carbons, I have 12 hydrogens, and I have 6 oxygens. Right, so I've got 6 carbon, I've got 12 hydrogen, and I have 6 oxygen. And I know carbon weighs 12 AMU, and I know hydrogen weighs approximately 1 AMU, and I know oxygen weighs approximately 16 AMU. So we can break down this chemical formula into 6 carbons, 12 AMU each, for a total of 72 AMU from carbon, 12 AMU from hydrogen, and 96 AMU from oxygen. And we can add that all up to get our total weight of approximately 180 atomic mass units for the whole molecule of glucose. So I'm just reminding you what a chemical formula represents, because today we're going to be naming things based on their chemical formula. And then a little bit later, we're also going to go from what is the chemical formula to how would I name this compound. So in this case, we're just talking about glucose. That's the common name for this. But a little bit later, we're going to look at ionic compounds, where we have got specific rules for naming those compounds. So the other important thing in this section is how to differentiate between ionic and molecular compounds. So molecules, there are 2 or more elements bonded together through covalent bonds. Molecular compounds, they're formed between a nonmetal and another nonmetal. Formed between a nonmetal bonding with another nonmetal. And this is why we broke down the periodic table, because right over here we have our metals. And over here in the green, here are our nonmetals. So one way to think of covalent compounds Okay, I need a nonmetal bonding with a nonmetal. I need something in the upper right-hand corner of the periodic table bonding with something that's also in the upper right-hand corner of the periodic table. Because with molecular compounds, we get an equal sharing of electrons in a covalent bond. That's different than ionic compounds. So molecular compounds, we need something from the upper right-hand corner of the periodic table bonding with another element from the upper right-hand corner of the periodic table. That is going to be your best way to distinguish what is a molecular compound from an ionic compound. Ionic compounds, they are a little bit different because they are formed between a nonmetal and a metal. Formed between a nonmetal and a metal. And so in this case, you've got something from the upper right of the periodic table and the left side of the periodic table. So right in the far left, we have our metals, and the upper right-hand corner, we have our nonmetals. So an ionic compound is formed between a nonmetal, which is found on the upper right-hand corner of the periodic table, and a metal, which is the left side of the periodic table. And what's unique about an ionic compound, we don't have a sharing of electrons. In an ionic compound, the metal will lose electrons, and the nonmetal will gain those electrons. Right, electrons are transferred. Whereas in a molecular compound, those electrons, they are equally shared. And so we are going to form an ionic bond between two oppositely charged ions, right? Last class, we talked about how ions form, right, through the loss or gain of electrons. We talked about cations, which are positively charged anions, through the loss of an electron. And we talked about anions, which gain electrons, forming negative charge. And so an example of this that we all know, right, sodium chloride. Sodium is going to react with chloride. The sodium is going to lose an electron, so it's going to become sodium plus 1, and the chloride will gain that electron, becoming chloride minus 1, and then the next step, we're going to get an electrostatic attraction between a positive charge and a negative charge, right, to form our solid sodium chloride. Right, so sodium being our cation, and chlorine being our anion. But the important thing is sodium was neutral, chlorine was neutral, sodium lost an electron, becoming sodium plus 1, chlorine gained an electron, becoming chloride. And then we have an electrostatic attraction between those two opposite charges to make our ionic bond in our ionic compound. So to identify an ionic compound, we're going to look for, do I have a metal and a nonmetal? Do I have something from the left of the periodic table bonding with something on the right of the periodic table? And so here's that reaction as it takes place. I've got my neutral sodium with its 11 protons and 11 electrons. That's going to lose an electron. And as it loses that electron, it becomes positively charged. And as the sodium loses that electron, chlorine is going to gain that electron. So chlorine also started as neutral with 17 protons, and 17 electrons. It gains that electron. Now it has 18 electrons. It has an extra negative charge now. And now we get our electrostatic attraction between our positively charged sodium cation and our negatively charged chlorine anion to form our ionic compound of sodium chloride. So again, today I said we would cover how to name ionic compounds. And I said you already know how to name ionic compounds because you know some ionic compounds. So ionic compounds, right, we're looking for a metal with a nonmetal. We're looking for something on the left of the periodic table that are our metals, bonding with something on the right of the periodic table are nonmetals. You name an ionic compound by giving the name of the cation, right, the metal. Metals are always going to lose electrons. They're always going to be positive. Our nonmetals are always going to gain electrons, so they're going to become negative. So you name an ionic compound by giving the name of the cation, followed by the name of the anion, and you're going to drop the ending of the anion and replace it with IDE. And so what this looks like, I've got sodium, and I have chlorine. You already know that's not the name because you know sodium chloride, right? So I name the cation as it would be as an element. So sodium as an element is still sodium. For the anion, the nonmetal, I'm going to take the ending, the INE, and I'm going to drop that ending and I'm going to replace it with IDE. And so that goes from sodium and chlorine to sodium chloride, where that IDE ending is what we change when we name ionic compounds. So the cation always goes first. The metal will always go first. The most metallic element will always be named first, followed by the anion. And the only thing we're going to do is we're going to change the ending of that anion by adding an IDE. Sodium and chlorine become sodium chloride. So here are a few examples for you to practice with. So the first one, I've got lithium and fluorine. That's going to become lithium fluoride. I've got magnesium and I've got sulfur. That's going to become magnesium sulfide. This one's a little bit tricky. Calcium and oxygen becomes calcium oxide. Got calcium and bromine. This is going to become calcium bromide. You should be able to go from a formula to a name and a name to a formula. So calcium fluoride. Well, calcium is right here in the periodic table and fluorine is right here in the periodic table. Calcium is group 2, so calcium should be 2+. Because calcium is 2+ and fluorine is a halogen, it's group 7, this should be -1. I would need to have 2 fluorines to balance out, right, the +2 charge on my calcium. So calcium fluoride would be calcium F2. Aluminum oxide, a little bit trickier. Aluminum all the way over here is group 3, so it's +3. Oxygen is -2. How do I get those to balance out? And so we're going to pick up with our next module on how to balance out these charges. But the quick way is by simply taking this number from aluminum, making it a subscript down here, and taking this number on oxygen and making it a subscript on aluminum. So aluminum oxide would look like aluminum 2O3. That's a quick way to get these charges to balance out. And if we break that down, I have 2 aluminums at 3+. I have 3 oxygens at 2-. So 2 times 3+ is +6. 3 times -2 is -6. For at the end of the day, a neutral charge. And that's what we're looking for. There is no charge to carry. So an easy way of balancing that out when we have odd charges that don't align is taking that charge and making it a subscript on the atom it's bonding with. So aluminum oxide turns into Al2O3.